Now, there are a few calculations we're going to use in this unit, and we call them the gas laws. Again, we could use them to mathematically predict the behavior of gases. The first one is called the combined gas law. The reason why we call it combined gas law is because it is basically Gay-Lussac's, Boyle's, and Charles' law, as well as Avogadro's law, combined into one equation. So it's taking four different relationships and smooshing it into one equation. And so what you see again is the equation itself. It's P1 V1 over N1 T1 equals P2 V2 over N2 T2. Say that 5 times fast, right? Basically, again, as you guys can probably assume, on the left side, the ones refer to your original conditions, what it is now. And on the right side, the twos refer to what it will be, or what the conditions will be after it changes. So we have what it was versus what it is, or what it's changing to. So what it says here in the note in bold is that basically the N stands for the number of moles, N for the number of moles. And you guys already know that pressure, volume, and temperature. Now, the way this works, because it is four different relationships into one equation, we don't always get every single variable in the problem. So let's just say, for example, that the problem makes no mention of moles. If the problem makes no mention of moles, do not include the n's. Leave N1 and N2 out. If the equation doesn't mention temperature in any way, or says temperature remains constant, well, if it's not changing from the first side to the second side, or from T1 to T2, then leave it out. You don't need to make up a number and keep it unchanged. That's just unnecessary. So we could have many different forms of this equation, whether we're going to leave out pressure or volume or moles or temperature or any combinations of those things. But basically, we're always going to be missing one thing, right? We're going to be given, for example, we might be given one pressure, but not the other pressure, but we'll have to be given, say, both volumes, right? So we're going to solve for the one thing we're missing. And in my example I just gave, we would probably be told that the temperature is constant, and again, doesn't even mention moles. So we just do the top part, P1 V1 equals P2 V2. We'd be missing one of those, and we use algebra to figure out what is the missing variable, kind of basically solving for X. All right, so let's try this. Again, that is also on the formula chart, of course. They give you the combined gas law for you. You do not need to memorize it. So number one, it says, if I initially have a gas at a pressure of, okay, notice, initially have a gas at a pressure. So that means this is going to be my P1, and a volume of this, so that's my volume, and a temperature of this, that's my T1, notice it's in Kelvin. And then I raise, so now we're going to the twos. Now we're changing things. And I raise the pressure to 14 atm and increase the temperature to this many Kelvin. What is the new volume? So we're looking for V2. Again, notice there is no mention of moles, so I'm going to leave moles entirely out of that problem. So now I just need to put it in that order. P1 is 12 atm. I'm going to multiply that by my V1, which is 23 liters. I'm going to put that over my T1, 200 Kelvin. And I'm going to do the right side is my P2, 14 atmospheres. My V2 is my X. You can either put X or V2. I like to use V2 because then I remember what I'm solving for. I'm solving for the final volume, but it's basically an X, right? And then again, 300 Kelvin. Okay, so to solve this, basically it's cross multiplication. Okay, simple cross multiplication. That's all there is to it. Now, I know it may look a little confusing, but it really isn't. What you want to do is the side that has all the variables given to you, you want to multiply that. Okay, you're going to multiply all that together. Then the side that has your X, your unknown, will be the denominator. That's what you're going to divide by. So for example, I'm going to pick up my calculator. Okay, I'm going to take 12 times 23 times 300. Then I'm going to divide that by 200 and divide that by 14. And I get V2 equals 29.571. And that is going to be in liters because remember, the unit of V1 is in liters. So again, what I did on my calculator, just to repeat, I took the diagonal that has all three numbers provided, right? So that's gonna be 12 times 23 times 300. Then I'm gonna immediately start dividing by the diagonal, all the numbers on the diagonal that has my x, in this case, my V2. So I'm gonna take that, divide 200, oops, I didn't hit divide. Divide by 200, divide again by 14 equals, and there's my answer in one single step, 29.571 liters. Okay, so that's the final volume if we increase the pressure by 2 atmospheres and we increase the temperature by 100 Kelvin. Okay, let's try the next one. So what we have over here is, let me change my color again. Okay, so we have a gas takes up a volume of 17 liters. So that's going to be our volume. It has a pressure of this, that's our P1, and a temperature of that, that's our T1. If I raise the temperature to this, which is T2, and I lower the pressure to this, then what is the new volume? Okay, so again, this is going to be kind of similar to the previous example in that we're looking for volume, the second volume, and again, they make no mention of the moles. So again, I'm going to leave those moles out of the equation entirely. There's no point in putting the number in if it doesn't change. Okay, so let me go ahead and plug this in. I'm going to put my V1, which is 17 liters, next to my P1. Now notice on number 1, I put pressure first and then volume. And on number 2, I put volume first before the pressure. It doesn't make any difference. When you multiply numbers, if you multiply 2 times 3 or 3 times 2, they both equal 6. It doesn't make any difference when you are multiplying which one goes first, okay? But the temperature must be on the bottom. Now, notice this is in Celsius, so we need to add 273. That would be 300 and what, 7? Yep, Kelvin. And then I'm going to take my, let's see, pressure 2, which is 1.5 atm. And then I have my volume 2, which is my x, my unknown. And then again, this is also in degrees Celsius. So that's going to be 323 Kelvin. So when I'm finished, again, I'm going to do the same thing. I'm going to go by the diagonal that has all three variables given, top left to bottom right. So again, 17 times 2.3 times 323 divided by the two numbers with the V2. 307 divide by 1.5 equals, my final answer is 27.425. Again, we're looking for a volume. That's going to be liters. So that's how you do the combined gas law. Okay. Again, the setup's pretty easy. I think there could be a lot of mistakes made when it comes to the calculator, how to enter it and how to do it in the right way, even though it is very simple cross multiplication. Again, it's not that hard to make some mistakes, and I'm sure some mistakes will be made. Number 3, a gas that has a volume of this many liters. So that's going to be my volume 1, a temperature of this, T1, and an unknown pressure, P1, has its volume increased to this, V2, and its temperature decreased to this. If I measure the pressure after the change to be 2.0 atmospheres, that again, that sounds intimidating, but really they're just saying that it's going to be changed to 2 atmospheres, right? If I measure the pressure after the change to be 2 atmospheres, well, it's 2 atmospheres. What is the original pressure? P1. Okay, so I'm going to put in my equation. I'm going to put V1, which is 28 liters, times P1, which again, we don't know, divided by my temperature, which has to be in Kelvin. That would be what, 318? Yep, Kelvin. Then this is going to be my V2, 34 liters, times its pressure, which was measured to be 2 atmospheres, over my T2, which again has to be in Kelvin. So that would be what? 308 Kelvin. Okay, so then my P1 So notice in this time, this is the diagonal that has all my numbers. So I'm going to take 318 times 34 times 2. Oops, I put in the 8 for some reason. Then I'm going to divide by both of these numbers that have my x or my P1. Divide by 28, divide by 308 equals, let me change my color, equals 2.507. Again, what we're looking for is pressure. Notice the other pressure is in atmospheres. So this unit would automatically be in atmospheres as well. You're not going to solve for a different pressure than what you start with. It's always going to stay the same thing. So again, I took the diagonal from bottom left to top right, multiplied 318 times 34 times 2, then divide by my shorter diagonal, divide by 28, divide by 308 equals, and there's my final answer. Number 4, if we have a gas has a temperature of this, T1, and a pressure of this, P1, if the temperature is raised to this, T2, and the volume is not changed, what is the new pressure? Okay, notice the volume is not changed. That means we don't care about it. We're going to leave it out entirely. So all we have is pressure. My P1 is 4.5 atmospheres divided by my T1, which again is 273 plus 14, so that'd be 287. Yeah. And then I'm going to have my P2, which I don't know what it is, over my final temperature, which is 273 plus 29. So that'd be 293.02. Yep, okay, sorry. My math is not always the best, ironically. Teaching chemistry, you'd think I was good at math, but nope. All right, so again, I'm going to go ahead and multiply my longer diagonal that I have both numbers for, 4.5 times 302. Then I'm going to divide by my shorter diagonal. So divide by 287. Again, my answer comes out to be 4.735. That again, we're looking for pressure. Notice in the problem, the pressure is atmospheres. So my pressure for this one will be in atmospheres. All right, the next one, what we have here is, all right, so the next one, it says, if I have 21 liters of gas held at a pressure of this, so that's P1, this is V1, and a temperature of this, T1, what will be the volume of the gas if I decrease the pressure and temperature to STP? Remember, standard temperature, standard pressure. There is no standard volume. So guess what we're solving for? Volume. So I'm going to go ahead and put in my equation. So volume is 21 liters. That's a funky L. Let's try it again. Liters. And then I'm going to put my first pressure, 750 kilopascals. I'm going to put that over my temperature, which is 900 degrees Kelvin. Then I'm going to, that's okay. Then I'm going to put in my standard temperature and pressure. Remember, standard temperature is 273 Kelvin, and our standard pressure when it comes to kilopascals is 101.3 kilopascals. Remember, that's from the formula chart. That is standard pressure in the unit of kilopascals. What that means is we're looking for V2 because remember, there is no standard volume. That does not exist. So again, just like I've been telling you guys before, I'm going to multiply by my long diagonal that I have all three. So 21 times 750 times 273. Then I'm going to divide by the other two. Divide by 900, divide by 101.3, and I get my answer of my V2 comes out to be 47.162. Again, volume. The other volume we were given is in liters, so this volume will also be in liters. So again, the only thing that was different about this particular problem is that they gave us standard temperature and pressure, STP. And again, this is standard temperature and pressure right here. Standard temperature in kilopascals is 101.3, and standard temperature is always 273 Kelvin, which is basically 0 degrees Celsius. All right, moving on. Number 6. Number 6, it says we have okay, so we have a hot air balloon has a volume of this, that's V1, and a temperature of this. What will be the new volume if the air is heated to this? So that means there is no moles. There's also no pressure. So my V1 is 1.00 times 10 to the 5th liters. I'm going to put that over my pressure, which is 298 Kelvin. Remember, that's just plus 273. Then I'm going to put my V2, because I don't know that, over my T2, which I don't want to mess this up. So let me just go ahead and do this on the calculator. 273 plus 65, don't laugh at me, 338. Whoa. 30, oh my gosh. 38 Kelvin. Sorry guys, it's reading my pen when I'm not even touching the screen. 38 Kelvin. All right, so I'm going to multiply the top left by the bottom right because again, I have both those numbers on that diagonal. So 1.00 second E 5 times 338 divided by 298 gives me V2 comes out to be 1,000, actually 113,422.819. V2 again, what we're looking for is liters. So that's going to be our final volume for this problem. Again, I like when they don't give you all three variables. They only give you, say, temperature and volume. It's a little bit easier. I definitely prefer that. Number 7. Number 7, it says we have the temperature inside my refrigerator is about 4 degrees. Again, that is the standard temperature of a refrigerator. That is common. If I place a balloon in the fridge that initially has a temperature of this, oh, okay, let me pump the brakes. All right, so it tells me that my refrigerator is 4 degrees Celsius. Okay, that again is not surprising. If I place a balloon in the fridge that initially has a temperature of 22, that is our T1, and this is our V1. What will be the volume of the balloon when it is fully cooled in the refrigerator? So this is actually V2, or excuse me, T2. We're actually going to cool the balloon down to 4 degrees, but it was originally at 22 degrees Celsius, which is about room temperature. So we need to be careful because everything we've been doing so far, the first 6 were pretty much in order. They gave us the initial conditions followed by the final conditions. And again, number 6 is just a warning that that is not always the case. So I'm going to go ahead and take my first volume, which is 0.50 liters. I'm going to put that over my temperature, which is 295 Kelvin. And I'm going to take my V2, which I don't know, and put that over my 4 degrees Celsius, which would be 277. Again, don't laugh at me. All right, I'm going to multiply, cross multiply, 0.5. Oops, I put one extra 0 in there. 0.5 times 277 divided by 295 equals my V2 is going to equal 0.469. And again, that's going to be liters because our other unit of volume was in liters. So it will also be in liters. Okay, number 8. It says, on hot days, you may have noticed that the potato chip bags seem to inflate even though they have not been opened. If I have a 250 milliliter bag at a temperature of 19 degrees Celsius, okay, then I'm going to leave that. So that's my V1. This is my T1. And I'm going to leave that in the car, which has a temperature of 60 degrees. What is the new volume? So My V1 again is 250 milliliters. I'm worried we have to change this into liters, aren't we? No, guess not. Then the temperature again, 273 plus 19 would be 292 Kelvin. I'm going to put V1 over here and T2, which would be 333 Kelvin. My V1, when I cross multiply, is going to be 250 times 333 divided by 292 equals 285.103. Again, volume. Our other volume is in milliliters, so this will also be in milliliters. All right, guys, there you go. That's the combined gas law. Remember, we're always going to be missing one number. That's like our x in algebra. We're going to do a cross multiplication to solve for it. But remember, if the problem does not give you moles, notice none of these did, then do not include in the equation. If it does not include volume, leave volume out of the equation on both sides. It's quite simple. We only use what we need, but the combined gas law is the relationship of all four of them combined into one. So we simplify it by using only the parts that we need, okay? All right, guys, again, thanks for watching about the combined gas law.